Alright, in my last video I showed the circuit boards that I made to control a bunch of devices around my house for home automation. And in this video I want to show how I built those circuit boards. I don't plan to do a tutorial in this video. This isn't like step-by-step, every detail, but it's the general idea from start to finish so other people on the same path who want to build their own electronics can maybe see where they should focus. So, if you don't know anything about electronics, then you need some basics. A good way to do that is with an Arduino. This is the Nano. It's small. You can find it cheaper than this elsewhere. There's many knockoffs. It's a microcontroller and a bunch of pins. You connect it to your computer and you program the microcontroller. A good first project is connect an LED and a resistor to one of the pins, write the code so the microcontroller turns the pin on and off, and you see the LED blink. This is super common. You'll find this on Google. It's really easy. You can use a calculator like this. This is the circuit, so power through your LED, through your resistor to ground. The resistor can also be before the LED, doesn't matter. So you enter your supply voltage. The forward voltage comes from your LED, your actual specs in your LED, or you can use this table for typical values, say like 1.25, and then the forward current that you want, say you want 4 milliamps, you need to use a resistor that's 937.5 ohms, or around there somewhere. That's how you build this. You can do this with a battery, then do it with the Arduino. This website's neat, it's called Falstad. This is a simulator, wires, and you connect the wires to a resistor and an LED, it lights up in here, and it tells you that this value resistor does this many milliamps. And it's a simulation, so you can simulate quite complex circuits. There's a bunch of examples here. If you reduce this to say 100, you'll see this is 37 milliamps, so it's probably too much. And if you made it like 0 or 1, 3.4 amps, so this is going to start a fire. So probably your 5-volt source can't give that much power through the LED. It's called a current limiting resistor. If an LED didn't have a resistor, it would draw too much current and burn up. So you need to add one. Once you get that working, slightly more complex project, I just Googled Arduino temperature sensor. This is a whole guide, shows you which sensor to buy and how to wire it up. This kind of diagram is not very good. It's called Fritzing. You see it a lot. There's a better way. If you struggle with this, just know there's proper schematics that are much better than this. After you do this, you might choose a different sensor. This is a temperature sensor, but there's all kinds of sensors like I use on my boards. There's other information. There's allaboutcircuits.com. There's tutorials and articles. This is EEV blog. This website is it's got a YouTube channel as well. And there's a forum. There's a bunch of projects. You can post. You can ask questions. And of course, ChatGPT. Using ChatGPT, it really helps a lot with electronics. It can help you find parts. It can help you debug your circuits. It's really great. You should definitely be using that. Once you've put together with a breadboard like this, or just wiring components directly, once you've done that a bunch, you're ready to move on to the next step. The next step could be proto board, where you're soldering to a board that has holes and copper around them, and you're doing through-hole components and soldering with an iron. But this is tedious, it's error-prone, it's a lot of work. There's a better way, and that's to have your circuit board made and shipped to you, and then you populate it with components and solder it with a reflow oven. To do that, the first thing you need is a schematic. So you'll need some software for that. This is DipTrace. There's other software called KiCad or KiCad. I don't know how to say it, but I don't really like KiCad very much, so I stick with DipTrace. There's also EasyCAD. I think it's a browser-based tool. I've never used it. There's Altium, which is a professional tool that's very, very expensive, like $8,000 a month expensive. DipTrace is free for small projects. It's really great. It's also very intuitive. I find it easier to use than the others. The first thing you need to do is bring in your components. That's these boxes and different symbols. There are many components, like some 100,000 something components that come with DipTrace, It's sort of a pain to find what you want. You can search for it. It's kind of slow. You can use this search at Snap EDA. So you put in a part number, you find a bunch of parts, and you can just download this, and it gives you the 3D model and the symbol for your schematics. It's pretty good, but you're trusting that whoever made this part did it correctly, and that can lead to problems. So you should really check this to make sure that the spacing and the size of the pads are what they should be, and that comes from the datasheet. To design your circuit, you need to know what's your goal, like what are you going to build, and then pick parts for it. So to pick parts for it, you go to DigiKey and you search for something. You get this parametric search. So you can choose different parameters and narrow down how many parts show up in the results. And then you can start to read the data sheets. There's a shortcut here for the datasheet and a datasheet link on every page. And then when you pick a part, you read the datasheet, see if it fits into your circuit properly. Reading the datasheet is a special skill. There's a lot of information here. You really need to learn how to go through this and at least pick out the things that are important, like the voltage of the part. This is a 3.3 volt part. In this one, I just want to show that it has a recommended land pattern. This is the size of the pad, 1.1 by 1.3, and they're spaced 0.8 by 1 millimeter here. So this is what you need to build in DipTrace. So you can try to download it and check the pattern, but it doesn't take very long, just a few minutes to build it yourself. And you do that in the pattern editor. DipTrace has these 4 windows: schematics, pattern editor, component editor, and PCB layout. It's just this, 4 pads. It's very simple. You give it a name, it gets saved into your patterns, and then you also create a component, which is just a named component here in the list, and then you draw a box and you put the pins. That's the pins for this particular part, the pin names, and then you click pattern and you map each pin to a pad. And that's it. That's the component. This is enough to do PCB layout for the pads and the schematic on this side. Once you've done that, you can just click on the component and put it in your schematic, and then you can wire it up. This particular schematic, this one is a microcontroller connector. There's a connector here, and it has connections to these 2 chips, which have connections to this connector that goes out to laser sensors. And there's 11 laser sensors, 5 and 6 on the 2 connectors. Those sensors, when you break the beam, they open a sliding door that's motorized. This is doing serial communication. It's doing it through these pins, RX1 and TX1, and there's also TX2 and RX2. The communication goes through these optocouplers, which I'll explain later, into this chip. And this is an RS-45 transceiver. We're going to need to go to the datasheet. You really need to learn how to read these data sheets and read them carefully. So use ChatGPT to tell you what any of the terms you don't understand are, and read it very carefully. Here's the description. Here's how it looks electrically. These absolute ratings, you know, if you give it more than 6 volts, you'll burn it up. So that's important. The electrical characteristics, this part is about RS-485. It's not super interesting for us right now. The supply voltage is 5 volts. You can see 4.75 to 5.25. So we need to give it 5 volts. That's pretty important. Switching characteristics, this is all nanoseconds and microseconds. It's about timing, and we're not too worried about that. These charts, this is what the designers thought was important for you to see. It's often something over time or timing information. It's good to read the titles of each one and try to understand the charts. Use ChatGPT to understand what they're talking about and what the chart might be about. Then here are test circuits. These are the circuits that they used to create those charts. So if one of the charts is actually important to you, you can look at the test circuit. That might be helpful. This section, these are the pins. This describes what each of the pins do. which is super important. This is how you know how to wire your device into the rest of your schematic. This table says when pins are in a certain state, there's something happening. This is the real meat of it. It describes in regular language, pretty much, how the thing works and what's important. This is super important to read. Don't skim it. Make sure you read it. If you don't, you can easily make boards that don't work. This particular board, it's half duplex. That means that it can send or receive. And it has auto direction. That means that if it detects someone sending, it will receive it. If it detects that you're trying to send, it will send for you, transmit for you. And these are the details of how that works. This little sentence here, there's a pull up and pull down resistor on A and B that are required. And if you don't use these, your device isn't going to work. This is crucial for this particular device. Moving right along. This is important. Typical application circuit. So this is nice. The designers of the chip show you how to wire it up with a few other components to get it to work. That's great, especially when this happens to match how you want to use it, and for us it does. On this side you have the microcontroller, and it's sending through this part. This is an optocoupler here and here, and it's receiving on this side. When it sends, it goes into the chip, and then it goes out on these A and B lines. And when it receives, it comes into the A and B lines and comes out this RO's receiver output back to the microcontroller for receiving. Some important things here, you can see the pull-up resistor here on A, that's pulling the A line up to 5 volts, and B, it's a resistor to ground on the B line, and there's another one between it called a termination resistor, RT, between A and B. Those are all important. You need all of that. This is a decoupling capacitor. On almost all ICs, these chips, you need a capacitor, a very small capacitor, physically near the pin, and it goes from power to ground, and then power to the pin. That removes noise from the power supply to the chip. Then it connects shutdown and receiver enable pins to 5 volts. And that just makes the chip turn on and makes the chip able to receive. This part, this is the optocouplers. The reason that they're doing this is your microcontroller can be a different voltage from the 5 volts that this needs. This separates that so that this can be 3.3 volts for our ESP32, and this side is 5 volts. The way it works is it's an LED. When this is ground, this is a resistor, power resistor, LED to ground, and it turns this LED on. This shoots light inside of the optocoupler to a phototransistor and closes this circuit. What happens is when this LED blinks on this side, this will see 3.3 volts or not, or ground actually. It's the opposite on the other way. So when this is turning the LED on, this is seeing 5 volts or not. And that allows the isolation between the two devices. We have the same thing here. It's flipped. So I have the microcontroller on the right, and then the two optocouplers, and then the transceiver. This is the decoupling capacitor, the termination resistor, pull-ups and pull-downs, and it goes to the connector. One last thing in the datasheet that's useful. This datasheet shows this diagram, which shows 4 chips and the connections between them. The important parts here is that there's a termination resistor on the start and on the end, but not on the devices connected in the middle. These lines can be very long, but the lines from those to other devices should be very short. These are called stubs, and they don't get termination resistors. It's very convenient that they showed how to connect multiple devices. Back to here, we have one more section. So this whole section is repeated There's 2 transceivers and it's all the same. And then this part, this is 5 volts from a barrel connector. It goes into a relay. And then out of the relay from here to all the lasers, all the devices below that are 5 volts. And this is done so that I can turn off all those devices with this relay. The relay is controlled by the microcontroller. So this pin comes from the microcontroller, power, and it goes into an LED and into a resistor and to ground, just like in the suggested beginner circuit to make an LED blink. When it turns on this LED, the relay completes this circuit. And that turns on all the devices and all the lasers work. And that covers this entire board. Before we move on, a couple gotchas here for the ESP32. These 2 pins, IO2 and IO12, they can't be high when the ESP32 boots. That means you can't have voltage on these pins. If you do, it won't boot and you'll be sad because you'll have to remake your board. The other gotcha is pins 34, 35, 36, and 39. Those are input only. You can't have them output a voltage. They can only receive. Those 2 gotchas are the main things that get people with the ESP32. Once your board is done, you move on to the next step, which is the PCB layout. Here is that schematic with the full layout done. But that's not so interesting. Let's delete this all and bring in the parts like we would be doing for the first time, and you get this big mess. The blue lines represent connections between the copper pads, and your job is to connect them correctly. It knows how they should be connected correctly because of the schematic. So you can be sure that if you connect it all and these blue lines go away, then it's connected correctly. That's a really great thing because if you are doing proto board and hand soldering it, you won't know it's done correctly. It's really hard to catch errors that way. You'll see when I connect 2 pads, the blue line goes away. The blue lines are called rat lines. Generally, the first thing you do is you pick a pad that you know is ground and you say hide net rat lines. That hides all the ground. And you do the same thing for 3.3 volts. And that's just to get rid of some of the lines because we don't really care about power or ground at this time. So the next thing you do is you start pulling the chips apart and building little islands of parts that need to be physically close together. The first thing you do is look at the part U2 and you see it has a decoupling capacitor. This needs to be close to this pin, C2. So you find C2 and you put it near that pin. You also want the ground to be near the ground pins and you can even connect it. So the reason you do this first is because it needs to be placed here. Nothing else can be placed here. If you do other layout first and then try to put your decoupling capacitors, you won't have room and you'll have to shuffle things around and create extra work for yourself. The next thing you do is find more components and move them close to the things that they connect to. And you just keep doing this until everything is close. Doesn't need to be perfect. You're just making little islands of parts. Once you have a few of these done, you'll see how the islands fit together and you can shuffle them around, change the parts in the islands. And once you have a pretty good feel that it's going to fit together compactly, then you can start connecting them and getting rid of the rat lines and making it all nice. Dip trace, getting your mouse in just the right place could be a pain, but it works. You see red circles, these are design rule errors. And that's because the silk screen was on top of the copper. That's usually something you do last. Eventually, you will have routed all of the traces and you'll end up with something like this, where it fits on the board. You draw a board outline and that defines the size of your circuit board. Everything fits on there. This board is a 4-layer board. This is the bottom. You can see it here. This is actually, I use ground on the 2 middle. This is not named well. The reason you do that, when there's many rules for routing traces, and one of the most important ones is to have ground underneath your trace. So the middle two, this is the third layer, this is ground, and this is the second layer that's also ground. And then the first layer has traces, the top layer and the bottom layer has traces. That ensures that every trace has ground underneath it. If you use a two-layer board, you have ground on one side and all your signals on the other side. Nothing can cross, because if you were to go to the ground layer and have a trace, it would cut across to another trace, and then that trace wouldn't have ground underneath it. So a four-layer board, it's much easier to make it a good board. Some people, they have one of the two internal layers power, and that makes it easier to just drop power anywhere you need it. These little holes, this is a via that allows traces to pass through the board to the other side. The via goes all the way through the board, through all of the layers. It's called a blind via if you only go partially through the board to another layer, but that's more expensive, so you won't be doing that. I don't need the internal layers to be power. I prefer it to be ground. And like, this is the power, this is 3.3 volts. It's quite easy to route this to where it needs to go without dedicating a whole layer to it. So for example, power goes through here, it goes into a via to the other side, and then it's routed up and goes into another via to this pin. So you might notice that there's these copper fills. Copper fills on the signal layers are not that important. There's many YouTube videos about that. The copper fills on the internal layers are important, and you see dip trace automatically connects things to the copper pores. Like this hole here is ground, and it's connected to this copper pore, which is ground. This is 5 volts, that's why there's 2 copper pores, and this is 3.3 volts. The way it works is just a polygon that you draw, and then dip trace does the rest. It's very convenient. Like if I have a trace that goes through the copper pore and I update it, dip trace automatically routes around it and fills in so that you don't need to do so much work. You'll notice that I put labels for every single component here, because later when I have tweezers and I'm putting these components down, it's much easier to populate the board when I can read it. I don't have to refer back to the schematic, and there's less errors that way too. Then the last thing I'll mention is the paste layers. If you get in close, you can see the brown outline for the pads, and that is the cutout in the stencil, which is a thin piece of metal that's going to go over this, and you apply paste to it, solder paste, and then remove the stencil, and it leaves the paste behind on all of the copper pads. Then you drop your components onto it, put it in a reflow oven, it melts all the copper all at once, and everything is soldered and your board is done. So that's the plan. It's good to check that all your pads have the correct cutout for their solder. If you have a pad that doesn't have a cutout, it won't be in the stencil, and then you'll have trouble when you go to solder it all. When you're all done, you can click on the 3D button, which is really cool. DipTrace makes this 3D model for you. It was one of the first programs to do that. This can show you the mechanical side of things, our components hitting another component, and you can't see it on the 2D view. You can also click Export Step, and you can export this as a 3D model. And that's super useful. We'll use that in a second to build the enclosure. That way we know exactly where the holes in the enclosure need to go. But for now, you just review it. You can use this to make sure that your markings on the board are correct. You see these markings R1, R3, C3. These are called reference designators, and they're just so that you can refer back to the schematic and see this is C2 and know exactly which component that is in the schematic. You don't have to do it, but it helps a lot. Even you're only doing your own boards, no one else is going to see this but you. It still helps. I'd still recommend it. And then one thing you need to do is put JLC 4 times. This text will get replaced with your order number, so stick it underneath some connector where you'll never see it. And then when you're ready to make your board, you go to Export, Gerber. There's many, Gerber, X2. You don't want anything except for just Gerber. On this screen, you might want to adjust the mask swell or mask shrink Otherwise, you can just leave it all alone. Click Export All. Zip archive Gerber plus NC drill is what you want, and save a zip file. Once you've done that, in a browser, you go to JLC PCB and you choose the zip file. If you make a 2-layer board, it's $2. A 4-layer board is $7. So pony up the $5. It's better. You should make a 4-layer board. If you change any of these, like the color, it takes more time. It can cost more. I think it's $16 to choose a different color for a 4-layer board. Other settings that you might want to change. Enig is a nice finish. It's very flat, and it's electro-nickel immersion gold. I think I got that right. It's not containing any lead. Hazel is, they put solder on and then they use a hot blade to cut it off. So you can choose that. With lead is cheapest, and this is most expensive. Like this had $16 to it. You don't really need it. And then the other thing that you want to check is specify a location. And that just means that the order number will go where you put JLC 4 times. If you say no, they'll pick a location for you. There's no cost for this option. If you say yes, they charge you $1. Then down here for stencil, this is so that you get the piece of metal that you're going to use to put the solder paste on. All these settings are fine. You don't need a framework. The default size is 290 by 190. And that is too large. So if you come up here and look at the size of your board, it's 55 by 59.5, so 55 by 60. So you say customize size. This doesn't have any cost. 55 by 60. Then you need to double one of these numbers because they're going to put the top and bottom on the same stencil. And then say add like 40 to each number so that there's a little space around the side. So now it's a lot smaller. If you don't do that, you're going to get this really big sheet of metal that's hard to store if you want to keep it. If we didn't check this one, then it would go back. So $7 for the board, $7 for the stencil, puts you at $14. And then shipping is like, depends where you are, $20 maybe, $25. Also depends how fast you want to get it. If you're willing to wait a month, shipping can be very, very cheap, and you can probably get the board for $20 or so total. One thing that's important is that the capabilities that JLC PCB has to manufacture boards are listed here, and there's a lot of them. A lot of things. This is like how close can holes be to other holes and all sorts of things like that. You can put a good deal of that into dip trace, into the layout, and that's done here under design rules. So these are clearances between like vias and traces, vias and pads, and these are the numbers I come up with for a 4-layer board. It's pretty close to their capabilities. I don't really push it. I use quite wide traces. That's also one of the mistakes most beginners make, is their traces are like the tiniest traces they can make, and it's just unnecessary. Don't make your traces too small. Sometimes the defaults, dip trace included, will be not so great. So if you're unsure, go ask ChatGPT or ask on the forums, Google it. Here are the other pages in case you want to see my settings. If you have this checked, enable real-time DRC. The DRC is the design rules, so design rules check. That is these red circles that show up. Shows you when there's an error. Sometimes it's pretty obvious, other times it's not so much. Like if you have a via too close to another via, it will circle it for you so you can fix it. If you do send something to JLC PCB that they can't manufacture, that's impossible, then it's a streamlined service, so they might just change it for you or make it anyway and then your board won't work, or they'll email you and then you can fix it. It usually takes like 24 hours for them to send you an email, and then you respond and then they respond. So it delays your order to have problems, and that's to be avoided if possible. So I would recommend not making your board yet. First, make your enclosure. We saved off the step file. You can go to a website like this, image to stl.com, and this will convert step to skp, which is a SketchUp file. So you do that, you upload your file, you download the new file, and then in SketchUp, you open the file. And it gives you a model that is what DipTrace generated for you. And the way these models work is you go here to 3D model, and by component outline, that means on your pattern editor for this part here, this box is on the layer for your component outline, which is here, and it just extrudes that by the height that you specify, and that's how you end up with this box. This height obviously comes from the datasheet for how tall this component is. This one happens to be very boxy, so it works fine. If you wanted to, you can give it a 3D model file. You could even make that with SketchUp. If you use SnapEDA to download, even if you change their copper pads to match your datasheet, if you use them to download, you often get a 3D model, which is very nice. And then in the 3D view, you'll have it. And then in SketchUp, you'll have it. The scaling of this is a bit odd. SketchUp has it in inches. So what you do is you change it to decimal and inches. Then you draw, this is the SketchUp way of doing this, you draw a line that say 10, and then you measure that line after changing it to millimeters. You measure that line, and then you tell it that that line is 10, but this time it's 10 millimeters because we changed the units. And it asks, do you want to resize? You say yes. That resizes everything down to millimeters. Everything's the right size now. So you can build a box around this in SketchUp. For example, here's one of my boxes. It took some trial and error to get these boxes just right, especially I started with screws, but found it to be inconvenient. It's much better for everything to just be snap fit. This holds the board, and this little snap keeps the WESP32 down there. The daughter board that we designed in DipTrace, it just plugs in, and that, with the connector sticking out of the side and it plugging in, keeps it in place. So I don't usually need any more snaps unless the board is very large. And then there's also snaps for the lid. These snaps hit these bumps, and they're quite thick, so there's no risk of that breaking. These are quite thin, so sometimes these break off if you're not very careful. And the material isn't very flexible, the material I use. Then I emboss a letter here. So since you know that the board is very accurate, you're sure that your enclosure is going to have the holes in the right place. I usually use 0.16 millimeters as a tolerance around the holes. And then I have some ridges that fit into here for strength over these long holes. Once you're happy with the enclosure, there's a plugin for SketchUp called Solid Inspector Squared. It doesn't like groups, and groups are the only way to stay sane when you're building your box. So I make a copy of the SketchUp file and delete the board, and then get rid of all the groups, so you have just the box and the lid. And then when you run this, you want it to say everything is shiny. If there's any problems like a reversed face or vertices that make a hole in your model, it'll let you know, because it's not 3D printable until the whole thing is sealed. Once you have it done, you need to export the lid and the box separately. So you go to Export 3D Model and export it as STL. Then you can go back to JLC PCB, and this time, instead of choosing PCB, we choose 3D. Choose the STL file, and it gives you the price. If you print it with SLA, it would be $4.38. The best material I found is called MJF. It's more expensive, so this brings up the price to $16 just for the lid. And printing the bottom part of the box is going to cost more because there's more material there. That's what the price is based on. If you're printing something very small, even in MJF, like my air conditioning adapters, then it's $1 per part. And then you always have to pick something here. So I just pick audio equipment enclosure, and then that's it. And you buy it plus shipping. It might cost $50 or $60 for one of the boxes. So you should be sure that your box is the right size and you don't have any mistakes in that, because it gets expensive. You could do tests with the cheaper materials. You can buy your own 3D printer too, but then it takes up space and you need to maintain it. I thought that JLC PCB's $1 million printer is probably going to do a better job. So finally, you have your board, you have your box. The last thing you need to do is solder all your components to it. The reflow oven that I use is this one called Controlio, and it looks like this. So yeah, $1,300 if you want them to build it for you. But this is all open source, and the software running on here is open source, and they give you this build guide. So if you want to spend the time building it yourself, you can. It takes about 6 hours or so. There's a lot of things that need to be done. It's based on a cheap, like $30 toaster oven, and then you add the electronics, the relays, the insulation. It takes quite a lot of work to get this into a really nice reflow oven. It can work even just like this. It's just not as good. So it doesn't have to cost you $1,300 though. They have these kits. The cheapest kit is $150. So if you have the time, the main cost is the screen and the board that they built. And then the software is open source for this. So it's really nice. It works super well. What it does, the controller heats up. Actually, there's a extra heating element that they add to the one they sell, but it heats up, and if you look in data sheets, you'll see often this solder profile. It heats up for a while, and then it lets the board soak in there for a minute or two, and then it jumps the heat up to very hot, melts the solder for, this is like 10 seconds, and then it cools. So in 3 to 5 minutes, your board has been completely soldered, and it's really neat. It saves you so much time. Like using an iron and hand soldering parts is super tedious. You may still need to do that if you have any through-hole parts in your design, but the reflow oven, nothing beats that. It's super convenient. So that wraps it up for this probably whirlwind of a video. I hope some of this was helpful. In the next video, I plan to show using the stencil, applying the solder paste, putting on the components with tweezers, sticking that in the reflow oven and melting the solder to finish the board. And then in future videos, I want to show putting the code on the devices and the code that runs to control the whole house and how that works together. So if you're interested in those videos, you can subscribe. Otherwise, I will see you in the next video.